Hello, everyone. So here we are, not in either of the lecture rooms. Why, I hear you cry? Well, those of you in section 504 know very well what happened in class yesterday as I speak. But I didn't worry too much about it because I knew I had a second chance in section 505. And indeed, our class in section 505 went just fine. People asked good questions. I was very pleased. Only thing that went wrong was I forgot to record it. So since I want to have a complete record of our semester's material, I'm more than happy to make this separate standalone lecture. So here I'm going to cover essentially the material that we talked about in class, again, yesterday as I speak. So as you'll recall, we began chapter 8. Chapter 8 is about alkene addition reactions. And that's a real hallmark, I would say, of how alkenes behave. They like to undergo addition reactions with a wide variety of electrophiles, as we'll see in this chapter. And there are plenty of reactions that we'll have to learn. However, all of the reactions have this in common. They're all addition reactions of this type. And here I just have a generalized scheme to show the nature of these reactions. And one thing I want to stress is that you're already aware that, that you're going to have to learn reactions in this chapter. You knew that from the first day of class. You'll have to know your reactions for our exams. Of course, these reactions are going to apply to exam 3, not exam 2, which we will be having imminently this coming Monday. But I suddenly one day realized, probably about the time I came here to A&M 5 years ago, that unless I make it clear to you guys what it means to know a reaction, then there's no way any of us can know that we're on the same page. So I would say, please refer to my class notes where I list a bunch of things that are the sorts of things you should be aiming to do when learning reactions, not just in this chapter, but in most all future chapters, both this term and next term, so that you make sure that you're learning the reactions at an appropriate level of mastery. The other thing I would say, near the back of the chapter 8 class notes, or maybe at the back, I have their handout or addendum that is something I developed with one of my former colleagues at my previous school, whereby we wanted to show students what they should do in order to make sure that they learn reactions thoroughly enough for exams. And it's certainly not the only way to learn reactions, but it is one way of doing so. Certainly, it's more than open to any kind of variations you might want to make on it, but it certainly should at least get you started. My experience is that doing something like that helps students best to prepare for exams. And honestly, that's what I did way back when I took organic chemistry before the earth cooled, you know, when there were only 5 elements in the periodic table. Anyway, but chapter 8 is about addition reactions to alkenes. And we already know of one. We know that you can take pretty much any alkene and treat it with HCl, HBr, or HI, and you will get a hydrohalogenation reaction. So for instance, if we took 1 pentene, Markovnikov's rule predicts that we will get 2 chloropentane as the product. And of course, this carbon over there, well, whoops, this carbon over here, we just highlighted, that carbon is chiral because it's sp3 hybridized and has 4 different groups attached. But I would predict that we would get a racemic mixture. The way I know that is because when I look at the reagents involved, which are just 1 pentene and HCl, I don't see anything that would control the stereochemistry of the product. I don't see any enzymes, I don't see any strange catalysts that might be able to do that for us. Nothing like that is mentioned. Therefore, I see no reason why the R enantiomer or the S enantiomer should be preferred over the other. And we would certainly get both, but therefore, statistically, I'd predict we'd get a racemic mixture. If we did the same reaction with 1-methyl cyclohexene I'd predict that we would get this compound. We might call that 1-chloro-1-methyl-cyclohexane. And that compound, of course, is not chiral. The way I know that is because there's a plane of symmetry running right down the middle that also bisects the chlorine in the methyl group. So this compound is not chiral. It is two groups effectively that are the same. So we're going to learn a bunch more addition reactions in this chapter. Another thing we're going to learn is how to prepare alkenes. And this topic actually will cover more in detail, I would say, in chapter 11. But alkenes can be prepared by elimination reactions, which is essentially turning an addition reaction on its head. And there are various reagents, depending, of course, on what X and Y are, that will cause the species to eliminate this molecule and form a carbon-carbon pi bond in its place. And just to give a couple of examples of common types of elimination reactions that yield alkenes, one can perform a dehydrohalogenation reaction. And of course, this chlorine could be bromine or iodine, or honestly, even with fluorine, it might work. Might not be the best way to do it, but it could very well work. But we will treat an alkyl halide of this type with some strong base. It doesn't have to be hydroxide. If it is hydroxide, the hydroxide ion is normally provided as the potassium or sodium salt in a nice polar solvent like maybe ethanol, though others would work too. And the major organic product here would be this alkene. We've already talked about Markovnikov's rule. Zaitsev's rule, we will eventually learn, predicts that if there's more than one possible alkene product in an elimination reaction, the major product is simply going to be the most stable alkene possible. And we already went over the order of stability of alkenes. This alkene is tri-substituted. If instead the alkene had been formed over here, or over here, it'd be the same thing at that point, that alkene would only be di-substituted. So I would predict with confidence this would be the major organic product. Certainly there will be some inorganic side products as well. Lots of times we don't even mention those. Now another way to form a double bond is through dehydration of an alcohol, and that's usually done with a strong acid. Sulfuric acid is very commonly used for such a thing. Phosphoric acid also will work, and generally this type of reaction requires heat. Phosphoric acid, if you really wanted to split hairs, is technically a weak acid, but it's just about the strongest weak acid there is. I think the pKa is around 2. You can double check me on that, but phosphoric acid is a pretty strong acid. So this would in general work really well. You will eliminate, in effect, a molecule of water and form the same alkene. And we'll learn mechanisms for this type of reaction in detail, mostly in chapter 11. Although you might even be able to make a very reasonable guess as to these mechanisms. They're not at all surprising. So bottom line so far, alkenes undergo addition reactions, and you can make alkenes from certain other species, like these and others, via an elimination reaction. So let's then move on to consider a couple more reactions that we're going to need to learn about in chapter 8. All right, and through the miracle of modern technology, we're back. So the first reaction I'd like to cover in chapter 8 that will be new to us is the halogenation of alkenes. Just as you can hydrohalogenate alkenes, meaning you add HCl, HBr, or HI, you can also halogenate them, meaning that we're going to be adding either Cl2 or Br2. And as you might expect from previous examples, F2 is much too reactive. It'll just destroy the alkene and tear it up into little pieces. You'd probably get nothing but things like carbon tetrafluoride, and then it would start to work on the glass. So fluorine is much too reactive. You don't get a controlled reaction with a predictable product. And iodine, as you might guess, molecular iodine, I2, is the opposite problem. It's too unreactive. If you were to add iodine to an alkene, they just look at each other. No reaction. No irreversible reaction, anyway. But chlorine and bromine seem to work just fine. This is also our first time focusing on solvents because one of the things you will need to know, as I've said in the class notes, for each reaction we learn is what a good solvent choice would be for that reaction. And there's often multiple ones. I would say for halogenation of an alkene, chloroform is pretty common. Some people are skittish about chloroform being allegedly slightly carcinogenic. Dichloromethane would also be fine, is a good deal less carcinogenic. I wouldn't go drinking it, but it's pretty benign otherwise. Carbon tetrachloride would also work, but that stuff is, if anything, more carcinogenic than chloroform. So, but any of those three solvents are fine, at least on paper. Now you will notice I'm also mentioning only the hydrochlorocarbons here. You might wonder if this can be chlorine or bromine, could maybe these be chlorine or bromine? And the answer is no, those compounds do exist, but they're a good deal more expensive. And I'm not even sure if bromoform is a liquid at room temperature. Carbon tetrabromide most certainly is not a liquid, it's a solid at room temperature. So the chloroform and dichloromethane and even carbon tet are a good deal cheaper and easy to get a hold of. Carbon tetrachloride less so these days, again, because it's somewhat less than benign. But like I said, on paper, any of those three solvents is fine. The product is, as you might guess, what you would get when you change the double bond to a single bond and then add halogen atoms of whichever halogen you're given onto each of the carbon atoms that were involved in the double bond. This is sometimes called a vicinal dihalide, which means simply that the two halogens are on adjacent carbons. Someone in one of my ill-fated 2 classes yesterday pointed out that vicinal is related to vicinity, and that's certainly true. Sounds to me like it comes from the Latin, at least that would be my guess. So, since we're going to start learning about solvents, I want us to get off on the right foot. What I would like you guys not to do when it comes to learning your solvents is just trying to memorize them, just trying to memorize a bunch of letters and numbers. Trust me, that will not go well for you. But if you understand some simple ideas, I would say, about what are good properties for a solvent to have, and you understand how those properties relate to particular common solvents. And I mean, it's not like we're going to be using 100 different solvents. I mean, there's probably going to be 5 or 6 that are the main ones we use in almost every case. So these here are not the only desirable properties for solvents, but they're probably the main ones. One that you might expect that makes a lot of sense that you want to be true of your solvent is you want it to dissolve everything, or at least almost everything. And the way you know that has to do with intermolecular forces. It has to do with polarity. It has to do with like dissolves like. So you would want your solvents to be of similar polarity to your reagents. And in this case, of course, elemental halogens are by definition completely nonpolar. Hydrocarbons are also quite nonpolar. So we would want something pretty nonpolar. And yeah, these molecules are a little bit polar, but not crazy so. They're nonpolar enough that they fit the bill. Interestingly, though you might not guess as much, dichloromethane turns out to be more polar than chloroform. I don't know the dielectric constants right off the top of my head, nor would I expect you to. But if you look it up, I think that's what you would find. Another thing that's usually desirable for our solvents is we want them to be a liquid under the reaction conditions. So this means you will need to know at least having a rough idea of the boiling points of the most commonly used solvents. And you'll also need to know that room temperature, since a lot of reactions are room temperature, not all, but a lot of them are. And generally, if it doesn't give a temperature, we usually assume room temperature. So we want the solvent to have a boiling point above room temperature, preferably well above room temperature. And room temperature in Celsius terms is generally rounded about 23 or 24 degrees, give or take, something like that. That's a nice, comfortable temperature, and I think the low 70s Fahrenheit. So, again, all of these compounds fit the bill, though dichloromethane's pretty close. Dichloromethane, I think, is a boiling point around 40. Chloroform, I think, more so like 70 or 80, and I would expect carbon tetrachloride to be even a little higher still, but they're all certainly liquids at room temperature. And I don't recall their freezing points off the top. Carbon tetrachloride's freezing point might be surprisingly high. The other two, I'm sure, are, you know, minus 80 or minus 100 or something silly like that you will never be doing a reaction that cold. So, but that does mean that you will need to know at least roughly what the boiling points are of most of the common solvents. And I think you'll find in general, the boiling points are going to be in general, you know, in the 40 to 100 range or something like that. So that over a reasonably wide range, the solvent in question is a liquid. Another thing that's very desirable for solvents is we don't want it to react with our reagents, at least not rapidly. And that's something that you're going to have to pay attention to as we go on, is having an idea of the reactivity of these solvents. And spoiler alert for these guys, reactivity is pretty low with alkyl halides. Yes, there are things that will react with them. We'll learn about them later. But there's certainly nothing here that's going to react with an alkyl halide. You need something a lot more reactive than either an elemental halogen or an alkene. Certain organometallic reagents, maybe, but these guys, no. So that's what makes these a good solvent choice. And to give two examples of such a reaction, let's see, I think I actually intended to make this chlorine, so we'll just do a little magic trick. There we go, presto. So if one were to treat 1-pentene with chlorine in, say, dichloromethane solvent or chloroform or what have you, I would expect the major product would be 1,2-dichloropentane. And of course, we are generating a chiral carbon here. That's something we made clear in chapter 5, that it's very possible to start with an achiral starting material and generate a chiral product. And similar to the one we saw earlier in this lecture, I see no reason why either of the enantiomers should be favored over the other. So I would expect you'd get a racemic mixture, 50% R, 50% S. This carbon here, of course, is not chiral. And the way I know that is the CH2. So there's no stereochemical implications for that carbon. But it's a little easier to see what's going on in terms of stereochemistry, especially if the starting material is cyclic, like this compound here, 1-methylcyclopentene. If we treated this with elemental bromine in one of those halogenated solvents, I would expect that we would get this compound plus the enantiomer, since again, you would get both. There's nothing that governs stereochemistry to the point of preferring one enantiomer over the other. But you will notice that our two halogens are trans to one another. And that will always be the case. It's true of the mechanism here too. It's just much easier to see in cyclic cases. So you would have this stereoisomer where the two bromines are trans, and the other stereoisomer where the two bromines are trans, basically switching both carbons and their absolute configurations. What you would not get at all is any of the compound where, or rather is any compound where the bromines are cis to one another. That you would not see as a result of this reaction. And that's all explained by the mechanism. So let's learn the mechanism next. The mechanism of halogenation of alkenes has two steps. In the first step, we have concerted formation of a three-membered intermediate. The way that works is the pi bond is going to swing out to form a bond to one of the two halogen atoms in the halogen molecule. Meanwhile, one of the lone pairs on that same halogen atom will reach out and form a bond to the other carbon atom that's involved in the alkene. And at the same time, we break that weak halogen-halogen bond. That's really the driving force of this step. Anytime you can break a weak bond and replace it with stronger bonds, that's money in the bank energetically. So again, I chose to show the bond swinging out this way, and this lone pair going that way. If you had done the opposite, it would be fine. I would not even notice the difference. In other words, the electron flow can be either clockwise or counterclockwise. And I don't see any way even of distinguishing that. I'm quite sure both happen in any real reaction. So either direction is fine. I would not even notice, which means you need to practice until you see those two possibilities as being the same thing. The intermediate that you get is known as a cyclic halonium ion, or a cyclic chloronium ion in this case. It's a three-membered ring, including a halogen atom, in this case chlorine, and that halogen atom has a plus charge on it. So as you can imagine, a very, very high energy intermediate. Not only do we have an extremely strained three-membered ring, we also have a halogen atom with a plus charge, which is not terribly happy. So the next step is not that surprising in light of this. We'll have a halide ion, which again may or may not be the halide ion that you just generated. Could be some other halide ion floating around. We'll attack the three-membered ring and open it. And officially, it's known that the halide ion will attack in the more hindered position. It wouldn't make any difference if it attacked in the other position with this reaction, because they're both halogens, so you'd get the same thing. But it is known that it does attack the more substituted carbon, and you will need to draw it that way for full credit. And also, when we learn about halohydrin formation, probably in our next class on Wednesday, then it's going to matter that our nucleophile attacks the more substituted carbon. Here you would get the same thing no matter which carbon it attacked. But it is correct to draw the mechanism showing the halide ion attacking the more substituted carbon. That breaks this carbon-halogen bond, releases all of that strain energy in the three-membered ring, and gets rid of the plus charge in chlorine in one fell swoop. So the reaction is two steps. First, formation of the cyclic halonium ion, and then opening that three-membered ring to give the dihalide product. One thing to notice about this mechanism is that there are no carbocation intermediates. True enough, in the halonium ion intermediate, there is some degree of plus charge on both of those carbons, but they do help the chlorine to bear the bromine to bear the plus charge. But there certainly is no carbocation as such. For that reason, we do not need to worry about Markovnikov's rule, which wouldn't apply here anyway, because one of our reagents is symmetrical, and we also do not need to worry about carbocation rearrangements. There is no carbocation intermediate, therefore no carbocation rearrangements. We can be confident about that. To show the mechanism of the other example, we have our 1-methylcyclopentene reacting with elemental bromine. Again, the bromine atom will use one of its lone pairs to form a bond to one of the two alkene carbons, whereupon the pi bond in the alkene will shift out to form a bond between the bromine and the other of the two alkene carbons. And again, I could just as easily have drawn them going in the opposite direction. Here I had them going, I guess, counterclockwise. Clockwise would be entirely fine. Not only would I not take off points, I would not even notice, as long as the arrows are drawn correctly. And again, we also break that weak, in this case, bromine-bromine bond. We get this cyclic halonium ion, and you'll notice that I'm being careful to draw this three-membered ring as being cis. And we've got a cis ring fusion with the five-membered ring. And that makes sense. You can only form a small ring like this fused to this other ring if the two bonds in question are cis. There's no way you can make it trans if one bond is reaching up here and the other one's reaching down there. They can't come together in order to form a three-membered ring. So you have to get a cis ring fusion. And of course, you will get the enantiomer of this as well, where the three-membered ring is pointing down and the methyl and hydrogen are pointing up. You would get that as well. In fact, I would anticipate a 50-50 mixture. At that point, our halide ion again will attack in the more substituted position. Again, there's no regiochemical consequence of that here, since both of those carbons wind up being attached to bromine. But for the record, that is what happens. Like I said, when we cover halohydrin formation on Wednesday, then you'll see it actually matters. That same principle, in other words. But when this happens, the halide ion has no choice but to come from the opposite side of the molecule to this three-membered ring in the cyclic halonium ion. That's sticking up in this case. And the bromide ion can't approach from that side because the three-membered ring is in the way. So it will instead approach from behind that bond, and again break this carbon-halogen bond, in this case carbon-bromine bond. When it does that, when it comes from behind, it's going to push that methyl group up. Later on in chapter 11, we'll learn this step is an example of what's called an SN2 reaction, and that's typical, that we're going to push this methyl group up, and we will wind up getting this compound, again, as well as its enantiomer. So the end result is our two halogens wind up being trans to one another. And again, that will always happen in cases like this. It's easiest to spot with a cyclic starting material, but that's the nature of the reaction. You will always get trans, or if you will, anti-addition of the two halogens. Good, so with that, I would like just to introduce halohydrin formation. We'll probably we definitely will wait until Wednesday, our next class, in order to cover the mechanism. So let's take a look at that reaction. Okay, and we're back, presto. So here is your halohydrin formation. I just want to introduce the reaction here and give a couple of examples. As I said, we'll save the mechanism for Wednesday when we get back after the exam. And the reaction corresponds really well to halogenation. The only difference is we've changed the solvent. Our solvent for forming a halohydrin will be water rather than an inert hydrochlorocarbon solvent. The difference is instead of getting two halogens attached to the two formerly alkene carbons, we'll get one halogen and an OH group. So this is actually one way of making an alcohol. This though happens to be a special kind of alcohol called a vicinal halohydrin. Vicinal, again, meaning that the halogen and OH group wind up being on adjacent carbons, and halohydrin referring to something that has both a halogen and an OH group attached. So just to give some examples, if we did the same reaction with 1-pentene, except instead of using chlorine in an inert solvent, we used water, water is now going to act as a reactant as well as the solvent. Now, this is not a very vigorous reaction. Water does not react terribly quickly here. It certainly reacts in a very slow and calm and methodical fashion, certainly calm enough to get one clean product. And I would predict we would get the species with the OH group on the more substituted carbon, the halogen on the less substituted carbon. And similarly, if we started with this alkene and used bromine and water, I would expect we would get this bromohydrin. Again, you'll notice the OH group is on the more substituted carbon. And furthermore, that the OH group and the halogen are trans to one another. So as you might guess, the mechanism's really similar to just straight up halogenation. There's just one extra step that involves a proton transfer so that we can get a neutral product out. But we'll save the mechanism for next time. So other than that, that's pretty much what we covered yesterday. So we'll leave it at that. Have a great day.